Yeah, risking the snow, we're getting trapped here tonight, so actually, yeah, it's a pretty good turnout considering. So it's my pleasure to introduce Nick Waber. Nick is currently in the process of doing his PhD at UBC. He did his BA and MA also at UBC and from the local MA Lithic. MA Lithic? Ah, I misread that one. So he's from the area and knows this area very well. In particular, his focus is on lithic technology, GIS, mapping, and the local archaeology of BC. He has done some field work in the last couple of years, working in Harrison, BC, working with the Sahelis, and he's currently helping them, teaching them GIS, and instructing them how to use it for looking at their local heritage. And presently he is a sessional teacher at UBC and teaching archaeological mapping. So he is going to present to us today on open source Lithics, so I'll hand it over to Nick, and yeah, thank you. Right on.
That's a lot to squeeze out of a thin CD. Alright, so yeah, today's talk, open source lithics. I'm probably gonna say the word open source a bunch of times. It's gonna be like the open source drinking game. Every time I say it, you have to eat a bite of cooking or something. Because that's what this is really about. The primary focus of my research is taking high-tech analysis methods and making it accessible to everyone, both in terms of use and in terms of affordability. So I want every researcher to be able to use something. This all stems actually from an SAA conference in San Francisco where Ben Marwick from, I think, the University of Washington made an interesting statement that for science to be science, it has to be replicable. And it's not replicable if you can't afford to do it. So, open source is about the fundamental replicability of research and analysis and science. So my talk, I'm going to touch very briefly on a couple current trends and relevant aspects of lithic useware analysis. And then I'm going to get into these methods I've developed. So one is the physical method. It's, I call it OpenHaft. It's an actual gizmo used for, I say quantifying gesture. That's possibly grandiose. Quantifying aspects of gesture. And then the other, a digital method for articulating 3D photogrammetry, the hottest thing in archaeology right now, with GIS for recording experimental lithic edgeware. And then at the end, I'll get into sort of the next step, the very beta mode, cutting edge, if I can bust out that pun. I have to not wear it out. It's not to wear out that particular pun. But the bleeding edge research of automating the 3D modeling with archaeological specimens rather than experimental specimens. So, my whole interest in this started actually with a friend of mine. She published this fascinating paper where she used focused variation microscopy to make very precise 3D surface models of edgeware on lithic artifacts. And so she was using these microliths, and she was cutting bone and antler and wood and flesh and hide and grain and stuff like that in 1,000 strokes, and then sticking these things under the microscope and coming up with these 3D models of the different wear surfaces. And to put in perspective how microscopic these are, each square is 10 nanometers to a side. So this is super precise stuff. Focused variation microscopy, for those of you who don't subscribe to Microscope Monthly magazine or whatever. Basically, if you think of a very shallow depth of field, when you look through a microscope and there's the little sliver that's in focus, but everything above and below is blurry. focus variation microscopy is that on steroids. It's a super thin depth of field, and by using the blurry parts, it basically creates a contour line that you can then create a 3D surface out of. And so by moving the object through that focal field, you get this lovely 3D surface. A similar approach is laser scanning confocal microscopy. And there it's basically microscope laser scanners creating 3D surfaces. So the reason I got so excited about this was looking at it, I'm like, oh man, that is just like a landscape. I wonder if GIS cares what scale things are at. Turns out it doesn't. She was using methods for quantifying roughness that are common in surface engineering. And I thought, what about quantifying roughness with GIS? That would be neat to try. I got to get my hands on one of these microscopes and take a crack at it. And yeah, so eBay's Google searches for confocal laser scanning microscopes and focus variation microscopes got me thinking about other methods of doing this. Then while I was, eBaying, I also got to thinking more about Danielle's experiment, where like I told you, 1,000 strokes, microlith, wood, 1,000 strokes, microlith, antler, etc., then you scan. And I sort of reread the paper, and she didn't define what a stroke is. And I'm like, aha! What is a stroke? Press F5, go to that one. The stroke is the most fundamental unit of gesture in any of these tool applications. And as a chain operatoire drum beater and materialism wonk, I totally subscribe to the statement. No tool is complete without the gesture used to put the tool into action. Anyone who's described an obsolete computer as a paperweight or a doorstop knows this. If you're not using the computer to compute things, the tool changes, the fundamental nature of the tool changes. And it's the same with lithics. You have to understand the stroke to understand the tool. So going back to the 1,000 strokes aspect of things, I started getting a little worked up. I'm like, what are the components of a stroke? And I sort of broke it down into two parts. There's the motion and there's the force involved. And so the motion is your direction. So if you're just doing a drawing stroke, that's one motion. If you're sawing, that's another. If you're scraping, if you're twisting, if you're boring, drilling, whatever, that is the kind of motion. And it has two parts. So if I'm sawing, so I've got my handy wood and antler props here, or if I'm sawing, say, that's about 2 centimeters across, so that's a 2 centimeter unidirectional stroke versus a 2 centimeter bidirectional stroke. In sizing, it's probably about a 10 centimeter unidirectional stroke. And so can you start to equate these dimensions of stroke with each other? And then there's the other half, force. As a married man with a taste for pickles, our house has debates that are probably echoed with many of you about what is the appropriate tension for the jar, for the lid on top of the jar. My wife quite unjustly uses the term welded to describe what she thinks is one end of the spectrum, and I quite accurately use the term resting gently on top to describe the other end of the spectrum. But this exemplifies two people using the same technology, using the same motion, because those pickle jars only have a certain amount of twist you can put into it, but using different amounts of force. So this has to be teased out in these experiments. If I hand a lithic to the local bodybuilder, fill him full of caffeine and have him do a test first thing in the morning, and then I give my grandmother the lithic and have her do the test after bingo or whatever, the results are going to be vastly different. And this has to be accounted for in the experiments. And so I started looking into it. conveniently, the world of engineering is on top of this. They know that these things matter, so they came up with the coefficient of wear. It's from a fascinating field of engineering called tribology, or the study of things rubbing against each other. And it's the coefficient of wear, so wear is the K, is the volume of material that is borne from a thing, from an object, over n is the distance of motion times n is the force. Specifically, it's the normal load. So if you think of, if I'm punching this table straight, that's the normal of this table. It's directly perpendicular in all directions to this surface, and that is the force we're talking about. So how to get these two things, especially, because we've got volume. That's what those microscopes are for. The microscopes are giving great data for volume, but we're ignoring the other half of the equation completely up to now. So how to get that stuff into our data? So the first part is the easy part, and that's the distance of motion. And calling it the lithic odometer is probably the closest analog. I've been using the term cumulative stroke length. I'm thinking of changing it to cumulative stroke distance. I'd love to hear your opinions. But it's basically just stroke count times stroke length. It's the same as the odometer on your car, which is tire circumference times revolutions equals distance traveled. And so this should solve that problem of the 2 centimeter saw versus the 10 centimeter stroke, where 5 motions like that should equal 1 motion like that in terms of the total tool use life experience. So the benefits, of course, are that it is really easy. It's an easy concept. I had to do a deep dive in the literature to make sure no one else had actually come up with it. The downside is it's very difficult to apply to strokes that are not lab-based. So if you are actually going to be making, say, a bone ulna, or ulna bone, that's kind of redundant, an ulna awl, then yes, this is great, because 99% of your strokes are either going to be incising for a very specific length defined by the ulna, or sawing, which is also defined by the width of the ulna. And so, yeah, you can record that no problem. It gets to be a lot more challenging if you're doing a more complex task. So if we were going to experimentally butcher a bison, that's a lot of different strokes at a lot of different lengths, and that's hard to do. Probably the best way to do it would be to film it, identify the different kinds of strokes being used, and then try to isolate those in the lab so you can get an idea based on that. But that's another ball of wax. I'll cross that bridge when I have a bison carcass. So, the other half is the physical gizmo. I call this the open haft. It looks like that. And it's a digital tool. I made it using all open source technology, so the hardware is open source. You can use different modules for it. You can make the module yourself if you have the chops with a soldering iron and whatnot. And what it does is it actually measures the amount of force that's being applied during any given task. If your tool has a handle and a business end, you can use this on it. You can use this to measure how much force is being used for rack levels, how much force is being used for paddle strokes, chopping, raking, whatever. In my case, because microblades are my thing, all of my experiments somehow end up with a microblade stuck to the end of it. In terms of precision, it gets about 10 grams of precision, which is really not too bad. It's precise enough that it can measure the weight of the tool on the end. Not very accurately, but it does register that something is attached to the end. It takes about 10 samples per second. Like I said, you can change different things. It beams everything to the computer. Designing it to be wireless was one of the major design considerations because I didn't want to restrict the stroke unnecessarily. If you have a plug stuck in there, you have to move differently because of that plug. It's like mowing a lawn with an electric lawnmower versus a gas-powered lawnmower. You don't mow over the cord, and that changes your behavior. So wireless, battery-powered, Bluetooth beams data directly to the computer. And best of all, it can be yours for the one-time price of about $60. And maybe an hour of soldering. So the way it works is all based on this. It's a microcontroller. It's a little circuit board called a Teensy, and that's the brains of the operation. It holds the code and controls the data and does everything. And that Teensy is paired with a load cell. The load cell is this aluminum bar here with a couple holes drilled through it. The aluminum bar has resistors bonded to it, and so the Teensy sends voltage through those resistors. When there is force being applied, when there's a load, that bar deforms very slightly, and the resistors deform very slightly, and that voltage changes. But that voltage changes in a extremely tiny way. So from the original, I guess it's 3.3 volt output, it's going to be getting marginally less than that back after this deforms. The amplifier increases that signal so that the Teensy can read it again, and then the Teensy can translate that based on this basically having been calibrated like you would calibrate any other scale into something that makes sense, like kilograms or newtons or whatever your flavor of load metric is. I generally use kilograms because it's the most easily expressible to folks. So then once the Teensy has that, it bounces it to the Bluetooth chip, which, as I said, sends it to the PC. So the Teensy itself is a really neat little gizmo. It's about the size of my index fingernail times 2 in length. It's, like I said, it's a microcontroller. It's effectively a tiny computer that can run one piece of software at a time. And the piece of software it runs is a bit of code that I wrote. There's an open source microcontroller that's extremely popular called the Arduino, and you may have heard of it. The Arduino is very widespread. It uses a computer language. I believe it's C, so it's not an obscure computer language. It's very popular, easy to learn, as demonstrated by an arts graduate learning it. And the Teensy can run Arduino code. All of the code, all of the hardware is free and open source. You could assemble the microcontroller yourself from other little chips and things and put it together if you want. Or you can just pay like $15 and get one yourself. The code itself, like I said, it sends the voltage, it reads the voltage back, reads the load cell data, and translates that, but it also does more. I set it so that I can actually determine the sample rate, so I can speed it up or slow it down as is needed. It applies an experimental timestamp, so I can synchronize it to video or whatever. I've been working on developing a motion tracking aspect to this, which will be vital with the timestamp. It tells you, of course, what the sample rate is, what your experimental set ID is, and I added a button recently that as you do each stroke, you hit the button and it'll apply a label to each stroke for subsequent statistical stuff. The data it puts out looks something like this. So this is an experimental set of 50 strokes from the pilot study I'll tell you guys about. And here you can see each data point in sequence. And as fascinating as that is, the nice thing about this not being a publication is I can kind of go off script and demo it. So give me just a moment here. I'll get this up and running. Yeah. So for the pilot study, as makes sense, I decided to move away from archaeological material. Not so much because I didn't want to do it, but because I needed more control. So I ended up using graphite. So the variables I would have are human gesture, specifically the load and the motion of the stroke. The controls I had, using graphite, is a constant medium. So I used actually both 2B and HB hardness of lead. So I had two different material grades there. Because it's a cylinder, that's right, you can envision in cross-section a lithic artifact is something like that. And so as you wear, you start from a very limited surface area, and even with a little bit of wear, that surface area changes. And of course that changes the relationship between the load, surface area, and overall friction. By using 2B graphite, which is just a cylinder, you know, as much graphite as wears off, it's always 2 millimeters. And that makes things really easy. It also makes things even easier in terms of calculating the volume, because when the radius is 1 millimeter and the volume is 2 pi r squared or whatever, the r squared is just 1. So that suits my mathematical skill just fine. So basically I did 1,000 strokes each, 2B graphite, HB graphite, heavy subjective pressure, light subjective pressure, subjective, as I say, as perceived by me, measured between each set of 50 strokes, and then charted it. So here's the load integral, basically. This is the load data. The integral is the space under the curve. So if you think of that XY axis, and that's what a stroke sort of looks like. You've got the maximum up here. You know, this is time. This is load. The whole area under here is the integral. And I picked the integral rather than average or maximum or anything like that because it's sensitive to both the maximum and the duration of the stroke. Because of course, if you're doing a longer stroke, you have more contact time. This is more of this expression of the use-life history of the artifact. So in this case, what you can see down here, we've got the 10 centimeter, 20, 10, 20, 10, 20, 10, 20. And all the 2B stuff is red, all the HB is blue. That will be consistent henceforth. The 10 centimeter is always having a lower load integral. This is for each set contributing to the box plot. And that's simply because it's a shorter duration of stroke. So changing that length of stroke changes the total amount of force that is being applied during any gesture. Shocking, I know. Well, you also get the maximums. So I don't know how many of you have used R, the statistical software, but it can pull out the maximums of curves very elegantly. And looking at the maximums gives a different picture. So comparing the totals, where you have HB and 2B very close, and for both the short and the long strokes. When you move to the maximum, it changes. These start to group now, not based on the length of the stroke, but based on the material that the tool is composed of. And so in this case, we've got the 2B, so the softer lead, especially with heavier stroke, is consistently lower in terms of the maximum force during any given gesture than the harder material. This ties into that beautiful Tim Ingold weaving the world type of model of cultural gesture and whatnot. in that tool use is reflexive. You're not just doing a gesture with a tool, or doing a gesture using a tool, you're doing a gesture with a tool. So you're actually adapting your gesture to the technology you're using. In this case, I'm backing off a little bit on the 2B lead, because if I peak up much more than this, I start breaking the lead. This has relevance to lithics, of course, because if you're using obsidian versus quartzite, you'll probably have a very similar example of this load being lower with a more brittle or more fragile material and higher with a more robust one. We get this a little bit, but not nearly as much with the lighter things. I should say the way I define light and heavy, light is enough pressure to draw a clear line. Heavy is just so much pressure that I'm not breaking the lead. So here, especially on the 10 centimeter stroke, you could see I was able to back off more and get a clear line with less effort. This has some interesting questions that it raises later on. So now look at the wear volume. So in this case, the y-axis is always the volume. X-axis here is stroke count. Down here, it's that cumulative stroke length. It's the odometer. So this is measuring volume using the method that every lithic experiment so far has used, which is just counting your strokes. And as you can see, it distributes 10 centimeters dashed lines, 20 centimeters solid lines, heavy, heavy, light, light. And it distributes pretty evenly, you know? No big surprise, it looks like we're getting about half the volume off the 20s off the 10. But if you didn't know that there was a difference between stroke length, you might interpret this difference as being due to different materials. When you correct for stroke length, the story, especially here in the 2B, is completely different. In this case, the 10 centimeter and the 20 centimeter track an identical volume reduction trajectory up until the 10,000 centimeter measurement point when the 10 centimeter one stops. So for the stats nerds out there, the R value for this regression line was like 0.98, which it doesn't get tighter than that. You know, there's more error than difference in the R value. So this basically, you know, like I say, it shows this 100% difference in cumulative stroke length equates to a 100% difference in wear. So that's this again, shown this time stroke count, and here's the intercept, where this actually meets when you correct for stroke length. This means potentially a lot of use for experiments that don't account for stroke length and say that we're identifying different materials in the stone tool wear. It's not necessarily different wear, it's not a different characteristic of wear, it's just not the same wear yet. So, and I think not the same yet is a distinction that has to be made from different. You know, these are different motions using identical materials and methods that are resulting in different wear. So yeah, that bounces over here to the cumulative load index and the wear again. So this is the heavy stuff, so it's the same as these plots, except this time it's the load integral cumulative over each experimental set. And so you can see it's that same trajectory as with the stroke length, but the gap happens, and that tracks out to be about the halfway point. And so this, I hope, illustrates that the relationship between the total amount of load being applied and the total amount of distance any lithic is covering is a really, really tight relationship, and one that can't really be ignored. So how to apply it? And I'm totally recycling this slide from past talks. I think Chris has seen it before. Is basically to do tasks and observe how they show up in the load curves. So in this case, I was using the same Microplate tool to process two different materials. The black line here is carving an apple, and the orange line is carving an orange. So, successfully comparing apples and oranges in terms of the gesture relationship in processing these resources. Interestingly, the apple, you can actually see different parts of the action in each of these strokes. You can see there's usually a dip in the middle. That's because your spherical things, as you carve, you get to about there, and then you reposition your left hand for the rest of the stroke. And that repositioning actually shows up in the data. So it starts to create a human-readable data wave, which I nerd out on in tremendous ways. The other interesting thing in terms of lab analogy is you can then start to compare these field gestures, because I'm carving an apple, I'm not doing 1,000 strokes of apple, to those lab gestures. So you'll remember the hard strokes, that is the peak range for the heavy stroke length for the graphite, and that is the apple range. It's a statistically insignificant difference between the two, and so it starts to show you can take these field gestures and move them into the lab. So what kind of stuff does this let us ask? I'm really interested in these two down here. The raw material, whatever. And Rudy's not here, is he? But the variation here, especially the task expertise, is what I'm interested in. I want to see expert butchers processing carcasses with stone tools, ideally after practicing with stone tools, or processing them with metal tools, or whatever. I want to see how expertise affects wear, because when you're doing a task, you don't necessarily use 100% of your strength for the task. You use enough strength, and expertise is what defines that word enough. And I think that this could start to move us into that direction, at least in terms of lithic experiments, where we can start to account for these aspects of gesture. So that's the fun physical part. Now onto the digital part, GIS for use-wear analysis. As I said, those landscaped surfaces at 10 microns in a direction really got me thinking about how to apply GIS to it. Conveniently, there's an entire suite of surface analysis tools ready to go in every GIS package. And so I'm using a basic concept called raster difference. And so if you think of a raster map, so every elevation, every DEM that you see in every GIS program, each pixel represents the elevation at that point, or it represents a data cell at that point. In this case, elevation. So here you can see how the pixels would more or less translate into 3D. So if you can take a 3D model of an unworn tool, slap it into the GIS, take the same tool after it's been used, and presumably has worn down a bit, so it's lost some of those pixels, or I should say those pixels have decreased in value, and you go A minus B equals C, you should come out with a handy little raster map that not only tells you that there has been wear, but quantifies the wear precisely in cubic millimeters. And it turns out it works. So the way I do it, because as I mentioned, I'm not buying any fancy microscopes, is I use 3D photogrammetry. I should also say the aspect that I work with doing this stuff should be classified as macro wear. It's the tiny flake scars, it's the edge nibbling, it's stuff like that that you get on stone tools. I'm not dealing with actual surface texture. I'd love to. I think it will work great for that. I just, well, I guess I do have the resource at UBC. I'm just not gonna. You know? Sometime down the road, I expect I will, but right now I find actually quantifying these microflakes to be very valuable. I also think it's valuable in terms of those micro-wear studies, because if you start with a microblade, you do a bunch of work with it, and so now you have flake scars coming off here, and then you stick it in a fancy microscope, and you sample here, and here, and here, and here. Each of these points has a different use life history. This is original surface, so it has experienced the total use life of the tool. These two are in flake scars, so they've only been getting wear since that flake scar came off. So you need to be able to identify the flake scars in order to tell what's happening. The other reason I like macro wear instead of micro wear is because the ancient people probably didn't care about micro wear, but they did care about macro wear. Macro wear is what defines dullness. When your edge wears down and isn't working as efficiently, that's when tools get, or that's often when tools get disposed of. So by being able to quantify macro wear, you can start to identify these very cultural notions of what constitutes dullness. If any of you maintain your kitchen knives and cook at a friend's house who doesn't maintain the kitchen knives, you know what I'm talking about. There are different standards of tools for different people, and it would be interesting to see how this translates archaeologically. Anyhow, in terms of the method, step one, 3D photogrammetry. If you're not familiar with photogrammetry, it's basically photos from different positions that turn into a 3D model. So the computer looks at each photo, it identifies common landmarks between the photos, so basically common pixel patterns, and calculates the angular relationships between those pixels. Based on those angular relationships, it can tell what the 3D shape is. Because of course, if you look at a cube straight on, it's just a square. But if you rotate it very slightly, suddenly it starts to have perspective. It's shorter here than it is here, it's shorter here than this was, etc. All of these different landmarks have different aspects to it, and the computer identifies those and stitches it into 3D. So for the microblades, I've got this macro setup. I built a little microscope stage out of a couple DVD drives pulled out of old Xboxes, and a little servo motor. And so I stick the microblade on there, and the stage moves very, very gradually, and I take a bunch of photos. I usually like taking about 20, it works with as few as 8. And then I get about 2 million three-dimensional data points for the microblade surface. And this is for a microblade that's like 1.5 centimeters long. So that's pretty good. One inconvenience about it, the software I use is called Micmac. It's free and open source, it's supported by the French Ministry of Forests, and the documentation is mostly in French, which I don't speak. More complex, Micmac used to be a doctoral project by a French grad student who thought it would be funny to name every process after a drink. And so nothing has a logical name. So for example, the photo distortion correction algorithm is called drunk. And so it's gobbling. Anyhow, it produces fantastic results. So this is the very tip of a microblade. And it's actually 2 scales. This is the 3D point cloud that has been aligned with each other. You have the original one out here in the smaller points, and then you can see in the larger points the worn surface there, and all that lost material. So we can start to track that in a very replicable and quantitative fashion. So the next step, since it produces those lovely points, each with an X, Y, Z coordinate, is to just slap it into a GIS and create a surface. You can use kriging or inverse distance weighting or triangulation or whatever you like. I find inverse distance weighting provides the best surfaces with the least noise, and it creates this. It effectively creates a landscape. I threw the contour lines on there more or less for fun. It gives you the volume and it gives you anything else that you want from this stuff. You can actually get edge angle based on slope. You can get aspect, so whether an edge is perpendicular to the primary dorsal eris axis or if it's sort of off at a different angle, all sorts of stuff like that, using your standard GIS tools. One complexity that I hit is basically quantifying where things are totally gone. If you have surfaces, so if you're just subtracting from somewhere where there's more material underneath, it's easy, it's just A minus B. But when it's A minus everything, you need it to go down to a common 0 point rather than go down to infinity. Because of the natural curvature of your average lithic flake, the stuff here from the middle at the edge when it gets worn away, and the stuff here from ends, comes up with a different value because there's about that much difference compared to the lowest point recognized by the software. So I basically had to learn how to digitally straighten lithics. Once again, borrowing from outside the box, it turns out there's all these hydrologists who digitally flatten rivers all the time. And so you can do the same thing with lithics. You basically just sample a whole bunch of points all the way around the perimeter, interpolate a surface between them that's basically a surface that mimics the curve and any twists of the microblade completely, and then subtract from that. And it turns into this beautiful, flat, uniform blade where the edge is always at 0. So you're always subtracting to the edge rather than to whatever else. So once all that's done to the surfaces, you just go to the next stage and you do your A minus B equals C. So here we have experimental microblade with no wear, experimental microblade with some wear up here, and then the volume of wear that changes. The black polygon actually marks material that was completely lost. So that's just tracked back to the original. So you can see where the flakes are happening. You can actually see the flake scars coming up onto the surface. And that's giving the wear in cubic millimeters. I should say, by the way, that the pixel size that I've been using is like 5/100ths of a millimeter. So it's pretty high precision stuff, even though it's not microscopic. Here's another image of that. This is actually a 3D rendering of that worn section. So you get a bit of that negative flake scar aspect happening there, which I find very exciting. You guys might not, but yeah. So one aspect of this that is really important to microblades in particular is this, and I'll get back to this. Which part of the edge is being used? Microblades as a concept kind of rankle. I have this statement that there's no such thing as microblades. It's like finding screws and saying you found a tool. No, you found the tool that holds together the tool. You know, the car isn't made of screws. You don't drive your screws down the street or park your screws. Same thing with microblades. The microblades are a component, by definition, of this other tool. In the BC interior, we don't have any intact hafts. We have end-hafted microblades at the mouth of the Fraser, basically, well, technically Strait of Georgia, one if you can straight, at Hoko River. We have side-hafted microblades, or at least I think we have side-hafted microblades at Namu. We have side-hafted microblades at Haida Gwaii. Those are hafted in a spear with the entire microblade edge exposed. And then when you pop up into the Arctic and the Northwest Territories, you have side-hafted microblades in a knife with a little cap over them, sort of like this one, where the base is capped. So there are three possible directions of microblade hafting influence, and we don't know which one was using, and each of these tools is vastly different. And of course that informs the gesture when we go back to the gesture aspect. So being able to map on experimental tools where is happening, which haft that's associated with, and which gesture that's associated with, and then look at the archaeological analogs is going to really help us reconstruct the hafts without having them. So the other thing I really like about this is, of course, if you go surface A unworn minus B, which is worn, equals C, and then you go, I believe, A over C, that creates a wear intensity index. Because wherever it's 100% worn, wherever A over C equals 1, that's complete wear. That's the total loss of material at that point. And everything down to 0 is everything in between it. So it scales out completely. So you can actually compare individual artifacts with each other and individual stages with each other in a more nuanced way than simply using lost volume. So this is that edge wear index, the same tool measured at three stages of an experiment. And so you can see the first stage, it's getting worn out here, and that whole bottom end snaps off. It's basically, if you're a flint knapper, it's like making a burin. And so that whole base just blew off. Kept working it, and you can see here is the side where it's really being worked. A bit more flaking off at the bottom end, but most of the wear is on the side. And then over here, the bottom end seems to have stabilized a bit. We're still getting wear on the side here, but suddenly the ventral surface, rather than the dorsal surface, which was getting more wear early on, is really starting to lose stuff. So if you think of that in terms of a progression, and you have ventral and dorsal, so the first flakes are coming off in that direction, which of course changes this angle. The next flakes come off in that direction. And it makes perfect sense, and it shows up in the data, which is the super exciting part. Now, you guys are probably like, oh man, well, this is a whole lot of GIS wankery that I'm not going to do. Well, the good news is the GIS program I'm using QGIS to do all of this, and it's free and open source and based on Python, and I'm writing this into plugins. So these plugins are downloadable by everyone for free and editable by everyone for free. So you can just scan in your Microblaze, and as long as you line them up, you just push a button and it does all this for you and comes out with your output. So this isn't the sort of secretive University of Oregon thing that they're doing with their bifaces, where they wrote their special ArcGIS thing. So if you're not in the hallowed halls of academia, after you drop your $35,000 on ArcGIS and all the extras, you have to somehow sweet talk them into giving you their secret software. This is open to the masses, loose in the wild type stuff. One of the other plugins that I've added recently is to actually make these comparable at assemblage scales. So, like I said, I wanted to find out about the BC interior and how microblades are being hafted. Well, instead of doing it each individual microblade and then making notes about where the wear is happening, I wrote a plugin that automates it. So basically, it puts a point in the middle, sends out rays, and wherever that ray meets stuff that's worn, and I define worn, I can just stick a threshold on there. So if I say the wear index, everything above about 0.25 constitutes real wear versus digital noise. It measures all of that and returns it as a handy spreadsheet. that then lets me take something like this multi-stage reduction process and plot it in timescales and in cumulative stuff. So here we've got that first stage where there was a lot of wear being lost at the distal end of the microblade, and then the second stage and third stage. This is all just the dorsal surface, by the way, so everything's sort of piling up on that left side. And so that lets you then take these assemblages and say, hey, are the microblades from Kamloops being hafted and used the same way as the microblades from the Similkameen? And you can just run both assemblages through it and compare these in terms of this coordinate wear thing. So I should say I didn't develop the idea for radially mapping wear. That was I think a South African group. If you're interested, contact me, I'll send you the paper. Yeah. So the way to do it then is to do experiments. Use this, record the wear, apply it to the wear index, so you can actually use your peak and integral wear to scale up or down the wear index for different users, so you can actually control for user strength on the same task. And then see what it looks like. Where is the wear happening? What is the intensity of the wear? When do you stop using a tool because it's no longer practical to use? You know, when is your sharp knife as impotent as a spoon? And then you can start to relate those different wear patterns to other things. What is the hafting style? What is the gesture being used? And so on. And then, of course, compare it to archaeological samples. And that's the hard part. You know, all of this stuff before has been kind of neat with the GIS, because it's like the Gold's Gym before and after photo of the skinny guy and then the buff guy, except going in the other direction. So doing the archaeological samples is a bit more difficult because we don't have the before photo. So how do we get that? And the answer being 2017 is obvious, or it would be if the physics community didn't let us down and didn't have Mr. Fusion ready. Instead, we have to make do with digital reconstruction. So if you think of an intact microblade, the microblade is used and there's some edge wear. Now the edge looks like that when you look down from the top. We have to figure out basically what is this missing volume. You can do it, and it's reasonably easy to do in terms of technical difficulty, just using 3D models and tracing and extending and stuff. There's a fellow named Kuhn who made the GIRF, the Geometric Index of Unifacial Reduction Flaking, in 1980, I think, and it basically did a version of this for unifacial tools, and then Met and Aaron more recently changed this to be a little more scientific and started using 3D imagery to do it, but it was a very manual process of taking the microblade or taking the tool at various spots and, you know, tracing and being like, okay, that looks about right, we'll extend to there, and it meets, and okay, that's it, and then you can start to calculate the lost volume. But I wasn't really happy with that, so I wanted to automate it, of course, in the GIS. So the first step, because you have volume on both sides, is to split the blade in half, and of course, you know, flip the bottom side over. And then start to just deal with the easy part, which is the triangle. So you have that bisector between the two edges, defining the bottom of your triangle. And remember, since we turned those microblades into digital elevation models, we have this dimension of the triangle as well. So we should be able to do a little trigonometry to figure out what the lost volume is. There are some tricky aspects to that, though. And the two tricky aspects, one is we don't know what this length is, you know, because both of these faces stop here. And two, when you look at the top down, we don't really know what the XY coordinate is. If you're just going straight out, that doesn't necessarily work because your slope isn't necessarily perpendicular to the dorsal arris. The slope of these different lithic faces could be going not quite any which way, but could be different. It could be something else. So I started looking into this, and this part of it wasn't that hard because, like I said, we have the DEM, so we can produce the slope. And the elevation slope, or the terrain slope from GIS, gives you that angle, it gives you this. And so you can just use your classic, I think it's grade 11 geometry. I don't know. I made it through grade 11 because I was a good basketball player, not because of any honest application of mathematical talent. But that will give you that angle, and because you know the elevation angle, you can figure out that distance and get that. So that's great. That gives you your vertical volume, but then you have to figure out where it is in terms of the direction from the point you're measuring from. And that was a little more complex. Here's the math for that. That took a lot of Googling, a lot of trial and error to figure out. And the tools I was using were, first I was using aspect, as this slide still reflects, and then I'm actually using distance direction in a distance matrix. So, first I used direction, then I used aspect. Because aspect, if you're thinking of, say, a terrain type thing, tells you what direction a slope is facing in. And that's exactly what we need here. And so I can use that aspect to figure out what the slope direction is, and then I can tell QGIS to use this coordinate and draw a line using that direction we got and stick a point there. So I wrote a plugin, and the plugin basically automates it. It creates a contour line around the lithic, and then it does those calculations and sticks a point close to the edge. And the question is, does it work? And the answer is a resounding sort of. It works in optimal situations. We don't always get optimal situations. And this, as I said, is the bleeding edge of this stuff. That pen somewhere. So you can imagine if all the lithics were beautiful triangles and this were straight, we'd be all set. The problem is that they're not triangles. They have that conchoidal fracture. That's why they're lithics in the first place, because that's how they fracture. So when you just use a straight face, that extends the slope down like that, and you undershoot the edge. And I go, okay, no problem. We can just take 3 samples, automate it to take 3 samples, and turn it into a curve. Yep, we can, but inconveniently, it's conchoidal fracture, not cylindrical fracture. So it's actually this elliptical shape that changes depending on where you are. So if you think of an ellipse, this is basically what this section of a lithic is like. And so the curve actually changes as you progress. And getting that is a nightmare, because when you just use a regular curve, it sticks you out about here. And that's where we want to be. So this part is still a work in progress. I'll get back to you, I'm sure. So yeah, once again, what kind of questions? And this is what I'm really interested in. What does sharp or dull mean to ancient people? How are people curating and disposing of microblades? You guys here at SFU, you've probably heard of Keithley Creek at some point, and some degree of social stratification and hierarchy and inequality happening there. Do the rich pit houses and the poor pit houses have different curation patterns for the same stone tools? Are the poor folks really squeezing every ounce of usable edge out of their material? After all, one of the drums everyone beats about microblades is they're this super materially efficient thing. Microblades equals scarcity because you can make them last. Well, what if that's not the case? What if people are throwing them out before they get dull, and microblades are actually an optimal solution to needing a really fine cutting tool? What if it's something in between? What if using the term microblades is the entirely wrong approach? What if we're just lumping all of these things into a single tool category because they're shaped the same, and we have to be more aware of function, and that function is defined by the use history? That's what I'm getting at. That's why these experiments are relevant, because we can start to get into those functional questions by doing these experiments, by creating different kinds of microblades through gesture rather than through lithic production, and hopefully answer some meaningful questions about the past. But that is for the rest of my career. This is just for my dissertation. Oh yeah.